You know exactly how this feels. You're a quant developer or an algorithmic trader, and you are just staring at your screen waiting.
Oh yeah, we've all been there, just watching the progress bar crawl.
Right. You've got this brilliant idea for a new signal, but your backtest data pipeline is absolutely crawling. I mean, when a backtest takes 30 seconds instead of 3, that's not just a minor annoyance.
No, it's a massive roadblock.
Exactly. It translates to 10 times fewer experiments per hour, 10 times fewer variations tested. It's the literal difference between finding a mathematical edge and getting completely beaten to the punch by a competitor who, iterates faster.
Yeah, that time penalty, it just compounds on every single hypothesis you test. You're essentially paying a massive tax on your own research cycle. And honestly, it heavily dictates how ambitious you're willing to be with your ideas.
It really does. And for over a decade now, the engine under the hood of that research cycle has almost universally been Pandas. It has been the de facto tabular data standard since, 2008?
Yeah, around 2008.
But let's be real about what 2008 was. Data sets were way smaller, hardware was totally different, and Pandas was designed for that specific era. Today, you are running Pandas on modern machines, yet it's still single-threaded, it eats up memory like crazy, and it completely lacks a query optimizer.
Which is wild when you think about the hardware we have now.
Right. Enter Polars. This is a next-generation library, written in Rust, executing in parallel, and built natively on the Apache Arrow memory model.
It's a fundamental shift in philosophy, really. We are moving from a tool designed for general-purpose data wrangling on older single-core hardware to a highly specialized engine, one built specifically to saturate modern multi-core processors with massive data sets.
Okay, let's unpack this, because we aren't just going to look at some synthetic, highly polished benchmarks from a GitHub README today.
No, those never tell the whole story.
Exactly. We are digging into real-world algorithmic training benchmarks. We're talking tick filtering, rolling indicators across hundreds of tickers, and parquet loading. Our mission is to show exactly where Polars beats Pandas, by exactly how much, and what the concrete real-world pitfalls are if you decide to tear up your code base and make the switch.
Which is crucial because there are very real pitfalls. I mean, it's not a magic wand. You just wave over an existing code base.
Right. It takes work.
But before we get into complex trading signals, we really need to establish a baseline with basic data manipulation. The sheer scale of the data set you're working with completely flips the script on which tool is actually superior.
Okay, the scale problem. Let's look at small data first.
Yeah.
Say 10,000 rows. In the quant world, that's roughly one instrument, one day of minute candles. Very small.
Tiny.
If you run a simple filter on that in Polars, you might actually find that Pandas is faster.
Which throws a lot of developers off entirely. They install Polars, run a tiny data frame through it just to test it out, and see a performance drop.
Wait, really? A drop?
Yeah. At 10,000 rows, a benchmark simple filter in Pandas executed in 0.18 milliseconds, while Polars took 0.32 milliseconds. So technically, Polars is slower out of the gate.
I mean, using Polars for a 10,000 row data set is akin to getting into a Formula One car just to drive to your mailbox at the end of the driveway.
That is the perfect analogy.
The sheer act of opening the garage, strapping into the 5-point harness, starting the engine, it takes longer than the actual drive. In Python, that getting in the car part is what's called the PyO3 tax, right?
That's a great way to visualize it. PyO3 is the literal bridge that allows Python to call down into Rust code. Crossing that bridge, translating the command from Python to Rust, incurs a fixed cost of a tiny fraction of a millisecond.
Which usually doesn't matter.
Exactly. On a massive complex operation, that fraction of a millisecond is entirely negligible. But on a tiny simple operation, crossing the bridge actually takes longer than performing the math itself.
But the moment you move past the mailbox, scaling up to 10 million rows, which is about 100 instruments over 2 years of minute candles, the dynamic changes completely.
Oh, completely.
The Polars advantage just explodes nonlinearly.
What's fascinating here is understanding the mechanism behind that explosion. Polars isn't just coded better than Pandas. It's fundamentally utilizing your computer's hardware in a way Pandas simply can't.
Because of how Python is built.
Yeah. In standard Python, there is a mechanism called the Global Interpreter Lock, or the GIL. Think of the GIL like a bouncer at a club that only lets one line of Python execute at a time, regardless of whether your computer has 2 CPU cores or 20. Pandas is bound by that bouncer. It's stuck on a single thread.
So it's using one core, while the other 7 cores on your laptop just sit idle doing absolutely nothing.
Exactly the problem. It's a huge waste of resources. Polars, because its core engine is written in Rust, bypasses the Python GIL entirely once you cross that PyO3 bridge. It natively utilizes all 8 CPU cores simultaneously.
Okay, wow.
So at 10 million rows, a group B operation in Polars takes just 100 milliseconds. In Pandas, because it's doing it sequentially on one core, that exact same operation takes 860 milliseconds. Polars is 8.6 times faster.
And for joins at that scale, Polars takes 120 milliseconds compared to nearly 1.5 seconds in Pandas. That's 12.1 times faster.
It's a massive leap.
And if we look at real-world ETL extract, transform load fat, the numbers are even more stark. Take the industry standard NYC taxi benchmark, which is about 12.7 million rows of data.
A classic benchmark.
Yeah. If you are reading that from a CSV file, Polars parses it in parallel on its Rust engine and hits a massive 25x speedup. It drops the load time from 28.5 seconds in Pandas down to 1.14 seconds.
I mean, dropping a load time from half a minute to 1 second completely changes the rhythm of your workday. You stop losing your train of thought while waiting for data to load. You stay in the flow.
But basic grouping and filtering, that's just the prep work.
Right, that's just getting the data ready.
In Algotrading, the real computational heavy lifting, the stuff that makes your laptop fan sound like a jet engine, comes from generating signals.
Oh.
We're talking about computing rolling indicators across hundreds of different tickers simultaneously.
This is where the structural limitations Pandas really reveal themselves. In a standard backtest, you need to calculate, say, a rolling mean, a standard deviation, or a z-score, and you need to do it across 100 or more instruments independently.
So you need to group the data by ticker symbol and then calculate the rolling math for each group.
Right. And in Pandas, you typically execute this by using the groupb.transform function and passing it a custom lambda function to calculate your metric.
Okay.
The catastrophic bottleneck here is that Pandas physically creates a new Python loop and often a new intermediate data object for every single group.
Wait, for every single one?
Yes, if you have 1,000 tickers, it spins up the Python interpreter 1,000 separate times. The overhead of asking Python to mediate every single step of that process is massive.
Okay, brace yourself for these benchmark numbers because this is where I actually did a double take. Computing a rolling mean for 100 groups, so about 100,000 rows total. Pandas takes 4,200 milliseconds. Polars takes 12 milliseconds.
It's almost unbelievable.
That is 350 times faster. But it gets crazier. If you have 1,000 groups across just 10,000 rows, Pandas takes 38,000 milliseconds. Polars takes 11 milliseconds. It is 3,454 times faster.
Yep.
Wait, 3,500 times faster? Is Pandas just profoundly broken, or is Polars pulling off some kind of dark magic?
Pandas isn't broken, it's just showing its age. You have to remember it was built in 2008 for single-core machines doing simple row-by-row analysis. What feels like dark magic is just Polars stripping away that Python interpreter completely.
So it bypasses the middleman.
Exactly. When Polars sees that group by and rolling operation, it doesn't spin up a Python loop. It hands the entire set of instructions to Rust. Rust compiles it directly into machine code, executes the grouping and the rolling math in parallel across your cores, and it completely skips creating those intermediate Python objects. There is zero interpreter overhead per group.
It's just raw compiled machine code crunching the numbers without the Python bouncer getting in the way.
You got it.
And even for complex technical indicators on a single ticker, Polars provides a massive edge. Like if you're calculating Bollinger Bands, Keltner channels, or the TTM squeeze, which is, a popular indicator that identifies market transitions from low volatility to expansion states, Polars consistently delivers about a 7x speedup over Pandas.
And I mean, a 7x speedup on a single ticker is great. But the moment you apply that TTM squeeze logic across an entire portfolio of 100 tickers, because of that grouping overhead we just broke down, that 7x speedup compounds into a 350x speedup.
Wow. So Polars is calculating these massive groups in milliseconds. But if your system is starving for data or like your RAM is completely maxed out, it doesn't matter how fast your CPU is computing.
Right, you just hit a wall.
This brings us to the engine room, because the way Polars handles data loading and memory is fundamentally different from Pandas.
Memory management is often the silent killer of backtests. We really need to talk about the concepts of eager versus lazy evaluation. Pandas is an eager executor.
Meaning it just does whatever you tell it to do right away.
Exactly. It processes every single line of code immediately as it reads it, and it usually creates bloated, intermediate copies of your data in memory along the way. Polars, on the other hand, is lazy.
Think of lazy evaluation like a master chef in a kitchen. An eager chef, that's Pandas, looks at step 1 of a recipe, walks all the way to the fridge, gets a whole carton of eggs, walks back, and puts it on the
A
counter.
lot of back and forth.
Yeah. Then they look at step 2, walk to the fridge, get a gallon of milk, walk back. It's a lot of unnecessary walking and wasted counter space. A lazy chef Polars reads the entire recipe first, from start to finish, before moving an inch.
Which is so much more efficient.
Right. They realize they only need half an egg and a splash of milk for the whole dish. So they go to the fridge exactly once, extract only what is needed, and use almost no counter space.
And in Polars, reading the whole recipe is done through something called a query graph. Before a single byte of data is touched, Polars maps out every math operation you want to do. This allows its built-in query optimizer to perform what we call pushdowns.
Okay, explain pushdowns, because this is where the real magic of data loading happens.
So let's break down the two main types. First is predicate pushdown. Let's say you have a massive Parquet file. For those unfamiliar, Parquet is a highly efficient columnar storage format.
Very standard in the industry.
Right. So your file has 10 years of trade data, but your Python code only filters for trades where the volume is greater than 1,000. Polars analyzes your query graph, sees that filter, and pushes that predicate, the filter condition, down into the read operation itself.
Oh, I see.
Yeah, it filters the rows out before they ever enter your RAM. Pandas, being eager, would load all 10 years of data into memory first and then filter it.
Which is exactly how you end up with those dreaded out-of-memory errors crashing your script.
Right, it just overwhelms the system. The second type is projection pushdown. If that same Parquet file has 20 columns of data, but your subsequent calculations only ever use the close price and the volume, Polars will only load those 2 columns. Pandas loads all 20. Thanks to these pushdown optimizations, reading specific data from a Parquet file in Polars is up to 4.5 times faster than Pandas.
And it's not just the loading speed, it's the sheer memory footprint. Polars natively utilizes the Apache Arrow format. Now, Apache Arrow is a standardized way to format columnar data in memory. Because Polars uses it, it can utilize zero-copy operations.
Zero copy is a massive architectural advantage. Normally, if you filter a data set in Pandas or move it between different libraries, the computer physically copies all those bytes to a new location in your RAM.
Which takes time and space.
Exactly. If you have a pipeline of 5 transformations, Pandas might create 5 physical intermediate copies of your data. Because Polars is built on Arrow, it just passes around a memory pointer. It basically hands Python a map saying the data you want is sitting right here without actually duplicating the bytes.
So a pipeline of 5 transformations in Polars uses 2 to 6 times less RAM than the exact same pipeline in Pandas. That is huge for retail quants working on standard laptops. And if you are dealing with absolutely massive data sets, say 100 million rows of high-frequency tick data that literally exceeds your physical RAM Polars, has a streaming engine. It processes the data in chunks on the fly.
Which is critical because when an eager system like Pandas runs out of physical RAM, the operating system desperately tries to keep it alive by swapping data back and forth between the RAM and your hard drive.
And that's thrashing, right?
Yes, thrashing. And it grinds your system to a near halt. By streaming the data in chunks, Polars completely avoids this virtual memory thrashing, yielding an additional 3 to 7x speedup over in-memory processing at huge scales.
So hearing all this, the multi-threading, the lazy query optimizer, the zero-copy memory, you probably want to jump into your terminal and pip uninstall Pandas immediately. You might assume you should rewrite every single line of your backtesting code in Polars.
And if you do that, you will completely ruin your backtester.
Here's where it gets really interesting. We just spent all this time explaining why Polars is a speed demon. Why on earth would using it break the backtester?
Because a backtest isn't just one type of computational problem. It consists of 2 fundamentally different parts. The first part is the data pipeline, loading the candles, calculating those rolling indicators, filtering the signals. That is massively parallel column-oriented work. Polars is an absolute godsend for that.
Okay, but the second part?
But the second part is the actual portfolio simulation.
The actual portfolio simulation.
Yes. The simulated order filling, calculating your running profit and loss, managing your dynamic position sizing. That logic is entirely path-dependent.
Path-dependent, meaning it's a strict chronological chain. Trade B's position size absolutely depends on the account balance after trade A completely finishes.
Precisely why parallel processing is useless here. You cannot simulate tomorrow's P&L if you don't know today's position. Core 1 cannot calculate trade 50, while Core 2 concurrently calculates trade 51, because trade 51 requires the exact mathematical outcome of trade 50.
It has to go in order.
Right. It requires a sequential element-by-element pass over the time series.
And Polars, being a highly parallelized, column-oriented engine, is fundamentally terrible at sequential element-wise operations.
It is not built for it. If you force Polars to do element-wise portfolio simulation using functions like apply, you will lose every ounce of performance benefit you just gained. This is why we have to look at the hybrid architecture used by serious production shops. Take the team at marketmaker.cc, for example.
Walk us through how they set up that hybrid architecture.
So they use Polars strictly for the data pipeline. It handles all the heavy lifting of loading from Parquet, generating the complex indicators, and filtering down to the core trading signals. Then, because Polars is built on Apache Arrow, they pass that refined data seamlessly, using that zero-copy pointer magic we talked about, so there's no memory bloat directly into NumPy arrays.
And once the signals are sitting in NumPy,
They hand it over to Numba. Numba is a just-in-time, or JIT, compiler for Python. Numba looks at your sequential Python loop for the portfolio simulation, and just before it runs, just in time, it compiles that loop into extremely fast, raw machine code.
so it bypasses the sluggish Python interpreter entirely for the sequential steps. Polars does the parallel data prep, passes the baton instantly via Arrow, and Numba runs the chronological simulation at C-like speeds.
That's the perfect synergy. It completely avoids the severe bottlenecks you see in older frameworks like VectorBeat, where Pandas chokes the initial data pipeline before the simulation even gets a chance to begin. By using this hybrid setup, marketmaker.cc measured a 6 to 8x overall pipeline speedup.
Which translates directly to research throughput. They went from running 500 parameter optimization iterations per hour to 4,000 iterations per hour on the exact same hardware.
That is the power of using the right specialized tool for the right segment of your architecture, rather than treating one library as a silver bullet.
Okay, so a 6 to 8x overall speedup is incredible, and 3,500x on rolling groups is genuinely mind-blowing. But let's ground this in reality for a second. Migrating a massive, entrenched quant codebase comes with serious friction. What are the concrete pitfalls of switching to Polars today?
The biggest headache you're going to encounter on day one is the lack of ready-made technical analysis libraries. If you are a Pandas user, you likely rely heavily on packages like Pandasta, which gives you over 130 technical indicators right out of the box with a single line of code.
And Polars doesn't have a standardized equivalent package yet.
It doesn't. You are going to have to build your own technical indicators using Polars' basic building blocks. Now, those blocks, things like rolling means, exponential moving averages, shifting columns, are very robust and concise. Implementing a Bollinger Band in Polars is only a few lines of code, but you still have to physically write it yourself, unit test it yourself, and maintain it yourself.
That's a very real-time investment. And we should reiterate the small data caveat we opened with. If your data set is consistently under 1 million rows, and you aren't doing heavy grouping across hundreds of tickers, you might only see a 1.5 to 2x speedup overall.
Which is nice, but
The weeks it takes to rewrite all your bespoke indicator logic simply might not be worth that marginal gain.
exactly. And even if you do decide the speedup is worth the effort, please do not attempt a rip and replace migration. Do not delete all your Pandas code over a weekend and try to start from scratch.
How should a quant pragmatically migrate then?
Do it piecemeal, because Polars and Pandas can talk to each other incredibly efficiently. Calling the toPandas method on a Polars data frame takes mere milliseconds because of Arrow's memory layout. So start by replacing just your your data loading bottleneck. Let Polars handle reading your Parquet cache or executing your QuestDB queries, where that zero-copy magic gives you massive instant benefits.
So you load data at lightning speed with Polars, convert it to Pandas in a millisecond, and let the rest of your legacy Pandas code run exactly as it always has.
Yes. Then, maybe next month, migrate your technical indicators to Polars. Leave your legacy portfolio logic alone until you are completely comfortable and ready to tackle Numba. If we connect this to the bigger picture, it's crucial to understand that Polars is not meant to be a one-to-one Pandas clone. It is a highly specialized engine for industrial-scale data pipelines.
So you shouldn't blindly expect that theoretical 3,500x speedup across the board.
Yeah.
Realistically, on everyday end-to-end pipeline operations, you're looking at a 2 to 10x speedup.
Which is still utterly transformative for a daily workflow. But it requires realistic expectations and very careful architectural planning around what needs to be parallel and what needs to be sequential.
Let's recap what we've discovered here. We've seen that Pandas, while incredibly foundational to the Python ecosystem, completely chokes on parallel grouping because of the GIL and interpreter overhead. Polars swoops in with Rust, hitting up to 3,500x speedups on rolling groups across hundreds of tickers by compiling directly to machine code. We explored the genius of the lazy query optimizer, our lazy chef, and how the Apache Arrow memory model allows for predicate pushdowns and zero-copy pointer passing, using up to 6 times less memory.
And most importantly, we established the architectural boundary. Polars isn't for everything. You have to pair it with a JIT compiler like Numba to handle the path-dependent sequential logic of actual trade simulation.
So what does this all mean for you? We are looking at open-source tools like Polars, Apache Arrow, and Numba, bringing C++ and Rust-level execution speeds natively into Python. 5 years ago, processing hundreds of millions of ticks and running 4,000 backtest iterations an hour required an entire team of data engineers and a massive institutional budget to build custom C++ infrastructure. Today, you can do it on a decent laptop in a coffee shop. The massive technological moat that large hedge funds used to have over independent quants, it's evaporating.
The raw infrastructure advantage is rapidly being commoditized by these open-source tools.
Which leaves us with a pretty profound realization. If raw speed and data processing power are no longer exclusively reserved for institutional players, does the future of alpha generation rely less on who has the best high-frequency infrastructure and entirely on who could ask their data the smartest, most creative questions? When a backtest takes 3 seconds instead of 30, you run out of excuses for bad ideas. The bottleneck isn't the pipeline anymore. The bottleneck is you.